It just says hydrogen deficient, but how much hydrogen there is, I don't know. That's a good question.
I found the seismology thing I wanted to show. Well, so I just sent on the chat a link to a paper, or to the nature thingy of the paper. If you look at that link in figure 2, you have the kind of profiles you can derive from seismology. So basically for that star, they have some frequencies. There's a table, but I don't know if we can read it from the website. Anyway, the figure 2 is the interesting thing.
Can you share your figure 2?
I can probably do that.
For those who can't get it.
Where's Zoom? It's here. Share screen. Yep. I guess it's this one. I guess it's this one here. Yes. Yeah, so basically the x-axis is the mass from, well, it's a tricky axis again, but it's the included mass in some weird transformation. So the core is on the left, the surface is infinitely far on the right, and you have the mass fraction on the y-axis. Yeah, nothing changes from 12 on, so don't worry. And you have the final fractions of CO and helium at the bottom right of the plot. Well, this kind of weird shaped profile is basically what they set in. So they wanted things with kinks and slopes like that. And every angle or every width in there is a free parameter that they were able to fit by trying to model the spectrum directly. So this is the kind of things they do for white dwarf seismology.
You can't write that.
What?
This made me laugh.
What's wrong?
Oh, it's just what you've written in the chat.
Oh, okay. Yeah, so that's it. That's the things they kind of do. That's all I wanted to say about this.
So the other, there's one other weird white dwarf that I think people should consider. Those of you working on explosions.
Stop sharing.
I don't think it was this one, but there was a paper in either Nature or Science a couple of years ago about a 0.3 solar mass oxygen white dwarf. I could dig out the link if anyone's interested, but you can find it probably easy. It should be easy. Now, 0.3 solar mass white dwarfs should be helium white dwarfs. Not oxygen, certainly not oxygen. They certainly shouldn't be carbon either. So the question is, how did this happen? And of course, binary C can't do it at the moment. Now, presumably it was some kind of failed explosion. So it could have been one of these hybrid cores where the helium blew up, took some of the oxygen with it and left 0.3 solar masses behind that didn't ignite. But then the question is, why not? Why wouldn't the whole star go back? And of course, it's hard to blow up a star made of oxygen because there's not really enough energy to do it. But you can calculate, if you convert all the oxygen to iron, how much energy you get out. You can compare that to the binding energy of the star, and you'll find that you don't have enough. But that doesn't mean you can't eject some of the star. The least bound layers you could probably eject. So, but as far as I know, nobody's really made any models of this. Alex, perhaps you know. I mean, you know more about the detailed modeling than I do.
Me? I mean, dangerous thing to suggest. But one thing, when you did say this mass, though, it did actually ring a bell. Not because I read anything about it. I didn't know this was a thing. I don't think anybody observed this. But yeah. My question to you is, do you remember if there was any iron at all in it, was observed near it? Because that's actually quite typical of the masses that some of the 2D models of failed accretion-induced collapses of oxygen cores get. So sometimes when they fail, they get a partial explosion. It doesn't collapse to a neutron star, and it leaves a very small, well, a potentially very small remnant, depending on the physics they decide is real.
Which progenitors are these?
So this is something like a failed electron capture supernovae, a massive. I'll find an example paper.
It's an oxygen neon core.
Yes, this would be an oxygen neon core that you started with. They end up with an iron-rich oxygen neon sort of core again.
I don't remember there being iron in the, or not significant iron. There was certainly, it was something like 99% oxygen. There was a bit of neon and some magnesium. There was no carbon detected, which is
interesting.
Weird. Yeah, it was a very strange object. And now that's not to say that this spectrum couldn't have been something else and they got it wrong. It's possible, but it might be something that we could look at is to look in, say, Gaia to see if there's many of these around, because they should be quite common, I think. At least if you have a sample of 1 billion stars, you should see some of these. They're low mass. Gaia should be able to tell you that. And if we have a progenitor model or an idea of where it comes from, we can estimate numbers and space densities. So that might be something for us to do. The question is, of course, what happens? Let's say you have an electron capture. When do you think it explodes? When do you think it partially explodes? And when do you think it doesn't really do anything? I don't know the answer to that.
Sensitive to the central density seems to be the critical one, and it's really sensitive to it. I'm just about to post the paper as soon as I find it. There we go. I'm just going to dump it in the Zoom chat just so everybody can see it. If this works. I never actually put it. Nope. Okay. Let's try that again. Desktop. Sorry, but yeah. So essentially, at least for this scenario, the critical parameter seems to be the central density. So if you're dense enough, and for example, massive enough, you will your electron captures will outpace the burning front of the oxygen, and you'll just collapse to a neutron star. If you are not dense enough, so for example, you're a lower mass, for example, which I mean in practice isn't really an issue for them because they don't consider. I mean everything's Chandrasekhar mass, so it's all microphysics. But if, for example, maybe you set off a sufficiently powerful detonation on a oxygen neon white dwarf, that's kind of why I was thinking about it. But yeah, if you weren't as dense, your burning front can outpace the collapse, and you'll incinerate the entire white dwarf and ideally unbind it. In practice, they actually don't fully unbind it. Where is it? They don't unbind it, and they're left with a small remnant, some of which they found to be around that mass, if I remember. But if I can just navigate through my file system, I'll send you the thing. Which, for goodness sakes. Okay, found it. Cool. I should have just looked it up on ADS. Feel free to continue discussion while I'm doing this.
I'm sorry, I was looking up the
order, and it's no longer ordered in this window.
Found the oxygen white dwarf paper, I think, so I'll send that out.
Awesome.
Okay. So my question then is, if it depends on the central density, can we translate that into just a mass?
I think that would be really, really, really hard to do, largely because it's so sensitive. You're talking about tiny variations in the central density can make the difference between a collapse and a partial explosion. That's originally I was thinking that. I thought, oh, okay, maybe, but it seems really sensitive. I've talked with a couple of explosions people about these papers as well,
Yeah.
they had concerns about the way they started the explosion. I'm sending it now. It's apparently quite large, but it should be visible now. So let me know if that worked. I've never uploaded something to the Zoom chat before, so I may have faffed it up. But yeah, so Bernard Mueller, for example, he had concerns about the way they'd started, specifically that they didn't start the explosion at a specific point, which he found a bit concerning. But other than that, I don't know. But yeah, as far as fundamental issues go, implementing something like this into binary C, the main problem I would see with it is that you'd be left with a free parameter for the central density in some regard. That would make essentially all the difference in the world to what I think you would actually see as an outcome.
Okay. That suggests that from any modeling point of view, it's going to be very, very hard to predict numbers of these things and properties.
Yes. Right now, I think it's very uncertain. Exactly. I don't think it's a well understood thing.
That's fine. So we could, but that doesn't stop other people writing things. So I don't think it should stop us either.
No, probably.
But we should be able to translate central density into as a function of mass. That should be just a function of mass. Well, I suppose as the white dwarf cools, it'll change as well. Probably not too much.
Yes.
You could. Well, Arman, you have detailed models of white dwarfs, right? So you could look into this. Sure. I wonder, do you have oxygen neon as well?
Yeah, I did some of those ones.
Okay, so maybe we could use those, and we could even put in the central density as a function of time for each of them, just in a table, and interpolate that. So I think we could get the data in there. That shouldn't be too hard. I mean, most of the uncertainties in white dwarf evolution are, sort of related to surface properties that people observe, but I can't believe the core density really depends too much on what happens at the surface. It's very hot in there. So.
No, perhaps not. Perhaps not. You probably could relate it just to the cooling track, maybe. I'm not sure what the relation would be, but it might be possible. Are you guys seeing my screen right now? Should be a
yeah. We see that.
Okay. So this is their summary table. So let's see. The CC, it's got it in there. Maybe it doesn't. All right, so I'm just trying to find the column that says whether it collapsed or not. But these are the sorts of central densities you're looking at, and the sorts of central densities that make a difference. It is quite sensitive to it.
That's the initial central density, right?
I believe it's the central. No, this is the central density at the point when the
when it initiates.
Went off.
Okay.
Yes. Yeah. I've forgotten what some of their acronyms are. I believe that's Coulomb correction, which they found it to be important, particularly for their remnant masses.
Yeah.
Yeah, here we go. Here are the mass remnant. So here's one that's 0.438, for example, 0.6. The Coulomb correction makes all the difference in the world. You turn it on, you double your remnant mass. So
wow.
Microphysics is important here, to say the least. I'll do that. Oh, I see. That was a different central density, though. This may have been one that collapsed to a neutron star, actually. I forget. I'll have to read over this again. But anyway, these are the sorts of, this is at least the data that they've put out. I believe there are other models that show a similar thing, though. So, yeah.
So I'm just reading that paper from Science that I sent you the link to. They say they link to a model that ignites at 0.3 solar masses in a shell, I guess a carbon shell burning, and then the carbon burning proceeds to the surface. Everything below it is just left behind.
Oh, okay. So you accrete. So you don't accrete. So you have like a carbon shell that has enough energy within it that when it is ignited. But how do you get the carbon shell in the first place? Like, do they just allow it to stratify?
I don't know the answer to that.
Right.
It's a good question.
Because usually your carbon and oxygen are pretty mixed up, right? And am I wrong? That was my impression.
Well, normally you have a carbon-rich layer and an oxygen-rich layer underneath. There is a bit of a transition zone, but it's quite sharp, and it's almost a step function. I guess that's what Gio was showing before.
Okay.
So if you can ignite at the base of that carbon layer, then you probably will blow off everything above it.
Right.
There's plenty of energy in there. So it's like a big nova, essentially, but a carbon-rich nova. So
Oh, hang on. Sorry, maybe I missed something. Was this inside a star or a white dwarf that they're saying this happened?
it's a white dwarf.
So that would be a very carbon-rich white dwarf then. Most white cuts, even CO white dwarfs, are mostly oxygen, aren't they?
Yeah, but you can do it. Well, yeah, okay.
I mean, because you'd only have 0.3. If you've got 0.3 masses of oxygen left, and you pretend it was a pure carbon layer, okay, maybe some of the oxygen was blown off as well. I guess.
Oh yeah, sure, yeah. But there must have been, because this thing is 96%. I think it is. They say oxygen. So where you have the mass cut between staying on the star and being ejected, I don't think that's easy to predict. So it's maybe, yeah, I don't know. Maybe. I mean, you could look at the energy that's released versus the binding energy, and that might be able to tell you. But
no, I don't think give that a read, though. It sounds like a very interesting object.
it's kind of a rough idea, but it could certainly work. Who were the authors? Oh, yeah. So that could be done. I think that I don't see any good reason why we can't do that. Yes, it's sensitive to the parameters, but that's okay. We can vary them. We have the capability to do that. So we can say what are the errors or the uncertainties. Could be interesting.